Good morning, my name is Mimi Chu.
My name is Joanna Ortiz.
My name is Stephanie Calle.
And my name is Juan Acevedo. Our mentor is Lily Lee, and our advisor is Professor Turner. And our project is on micro-cantilever-based sensors. I have with me a mini watermelon. What are some ways in which we can detect this? We can all see it, touch it, if we cut it open, smell it, taste it, maybe even hear it. We all have 5 senses in which we can detect things in this world, but we can't detect everything. That's when devices are developed to help us detect these things. For example, food contamination can be detected through certain devices, explosives, and drugs and weapons at airports.
In addition to those devices, we have a smoke detector. As many of you know, it is able to detect carbon monoxide in the air. Lastly, we have current devices that are being used to further cancer research, and they're able to detect certain biomolecules. These devices are great and awesome, but there's one device that's very small, and it can be more efficient, more ultra-sensitive, and less costly. That device is called the micro-cantilever device.
Before we can even develop a device that uses micro-cantilever beam, we have to study the mechanical properties of the micro-cantilever beam. When we hear beam, we think of the beams that are used for supporting buildings, and they're several feet long. While this micro-cantilever beam is at the micro size scale, is about 1/5 of a millimeter, half the diameter of the human hair. The way we use the application of as a detection device would use the micro-cantilever beam as an oscillator by using its natural frequency. An example of natural frequency is the vibrating motion of a guitar string. So by plucking the guitar string, it vibrates or oscillates at its natural frequency.
So all beams or spring mass systems have a natural frequency. Natural frequency is the frequency where it's most comfortable with, and it wants to stay there. We can see this in this plot, amplitude versus frequency, and we are able to know where the natural frequency is, which is at its peak, and that correlates with the maximum amplitude as well. We can also see that in this equation to the upper right corner. Omega is equal to square root of K over M. Omega represents the natural frequency, K represents the stiffness of the beam, and M is the mass of the beam itself and any other mass attached to it. So many of you guys are probably wondering what exactly is a micro-cantilever. You all know it's very, very small, and you can see it in this picture. We are able to coat it with a certain material or certain chemical that is only able to react with another certain chemical. For example, here, this red coating can only react with the magenta blocks. Let's say these shapes are all gas molecules. So if they react, we can see from the equation that if mass is added, the natural frequency is changed. This shows the shift in natural frequency. With this shift, we can know if that certain particle is present.
Our project goal is to study the idealized model by using spring mass systems. We need to study spring mass concepts so that we can understand the behavior of the micro-cantilever beam. And also to learn the mechanical properties of a micro-cantilever. Here you can see a picture of micro-cantilever, which is a really small device. Our last goal is to analyze the data by using MATLAB program. So MATLAB program is a program that can be used to do calculation and to make some graph.
The data we obtain all begins through the use of a computer program. This computer program initializes a voltage and a certain frequency, which is prompted to the function generator. A frequency sweep occurs in which frequency is constantly increasing, yet the voltage remains the same. This is applied towards a piezoelectric material. The reason being is piezoelectric material has certain properties in which voltage is applied to it, it deforms it. The device of the micro-cantilever is set on top of this device. The piezoelectric material deforms and helps the device oscillate. This whole thing is then put underneath the microscope.
This microscope is attached to a laser vibrometer. The laser vibrometer shoots down a laser beam to the micro-cantilever, which sits on the device. The beam shoots back up, and the laser vibrometer reads it. The laser beam is Doppler shifted. The frequency of the laser beam is Doppler shifted, and the laser vibrometer is able to represent velocity in terms of voltage. This data is then sent to the spectrum analyzer. The spectrum analyzer reads the voltage and is able to give us an amplitude versus frequency plot. From the plot, we are able to see where the natural frequency occurs. We repeat the process many times at different voltages, and that's our experimental process.
So this graph shows the frequency response at different voltages. We try to find the natural frequency of the device. During the frequency sweep, we can see that the larger amplitude it responds where the driving force is closest to the natural frequency. As the voltages increases, the amplitude also increases, but the frequency doesn't change, which means the system is linear. We need to drive the device harder. So because the higher the higher the amplitude, the higher the ratio of the signal to noise. However, there is a limit on increasing voltages. If we drive the device too much, we can see in the graph there is a frequency shift to the right. Starting from 3 volt, the frequency shift to the right. So that means the system is nonlinear.
Another observation we made about the mechanical properties of the cantilever beam was by conducting in the linear response using 1 volt, exerting 1 volt, where we see when we conducted frequency sweep in increasing order and also in decreasing order, the curve follow the same path. There is no path dependency when we're in the linear response. Now, we conducted the same process with the frequency sweep and the nonlinear response using about 10 volts. So when we conducted the frequency sweep in increasing order, the curve followed the red path. And again, when we decreased the frequency sweep, it followed the black path. This illustrates right here, this gap illustrates that the curves are path dependent, also known as hysteresis. This graph is illustrating hysteresis of these curves. So our results show by analyzing our data or our plots that the harder we drive the cantilever beam, the more voltage we apply to it, the larger the amplitude at each voltage. Another observation we made is that there is a maximum to how hard we can drive this device, and this occurs about 3 volts, where it becomes nonlinear. And the last observation we made was that at a non-linear response, meaning where we drove the cantilever beam too hard, the system is unstable.
So in our experiment, what we did is we looked at the mechanical properties of our micro-cantilever, and we analyzed certain plots or charts to be able to describe its nature. The reason we did this is because we wanted to get a better understanding of how this device actually works and how it can help us. Many of you in this room are probably affected by certain diseases or cancers, just such as Parkinson's disease or prostate cancer or AIDS. And we're hoping that with this device, we are able to maybe even prevent those diseases. So the micro-cantilever is an oscillator that will hopefully help us as a society as we oscillate into our future.
We'd like to thank our mentor, Lady Lee, and our advisor, Professor Turner, the faculty and peers, all the resident assistants, and then all of you for coming and giving us your time. Thank you.